So good morning for everyone, and we start a new day of open readings, and it's my honor and privilege to introduce you Professor Jonas Žmuidzinas from Caltech Optical Observatories from the United States, California. So Jonas graduated Caltech in 1981 and got Ph.D. degree from University of California and Berkeley in 1987. So then he was associated with Jet Propulsion Laboratory and involved in many projects related with submillimeter astronomy. So as he says, I like find astronomical problems that demand technical innovation for their solution problems that cannot be solved existing technologies and instruments. New technology and instrumentation open up new possibilities for discovery. So Jonas likes challenges and likes interdisciplinary approach, something between physics, astronomy, and engineering. So he built first instruments for astronomy during his PhD at Berkeley, then and returned to Caltech in 1989. He was involved in many astronomy projects, including instruments development for Herschel Observatory, which was the biggest infrared observatory up to the launch of James Webb Telescope just last year. So during his investigations, he developed unique instruments dedicated not only for Herschel, for SOFIA projects, also his devices named superconducting detectors suitable for large arrays, later published in Nature, is a main detecting instruments in Atacama Observatory in Chile, which is using 25 diameter telescope for radio astronomy. Beautiful devices like on-chip spectrometers for millimeters and submillimeter waves. Heterodyning instruments for Herschel for far infrared range, wideband low noise superconducting amplifiers with high dynamic range, purely dedicated for astronomy, unique instruments with containing beauty of physics and having extraordinary application. So work is highly interdisciplinary. So today, we also expect something amazing between physics, astronomy, and engineering. Professor Jonas Žmuidzinas, Caltech, California.
Ačiū, Gintarai. Thank you for the introduction. It's a pleasure to be here. I won't describe anything that Gintaras was just talking about. My topic today is entirely different. I'll be talking about the Caltech Optical Observatories. I've had the honor and privilege of serving as the director of the Optical Observatories at Caltech over the past 5 years. So I'll be talking about that and about the history, about some of the recent projects that we're doing. So something different. Let's get going. So first of all, what are the Caltech Optical Observatories? Caltech has the Palomar Observatory in California. The most famous telescope there is the 5-meter Hale telescope, also known as the 200-inch telescope if you use English units, and therefore, in short, we call it P200. I'll be using that term. But then in addition, on Mauna Kea in Hawaii, there is the Keck Observatory, which has 2 10-meter telescopes. This is a partnership between Caltech and the University of California. So I'll be describing the work that's going on there. And then in the future, we're hoping to build in partnership with not just University of California, but a number of international partners and even larger telescope. This is the 30-meter telescope project. I'll say only a little bit about that, but give you some impression of what that is. So we're going to start with Palomar. Here you see a photograph, aerial photograph of the observatory. Of course, the largest dome that you see is the 200-inch that I just described, but there are a number of other telescopes. They're labeled by the size, starting from the smallest, P18, 18-inch, which is in fact the oldest one. There's a P48, P60, and then in the foreground, of course, the P200. If you look in the upper right, you'll see a map that shows the location, roughly halfway between Los Angeles and San Diego, in the mountains in the Cleveland National Forest in California. Below that, you'll see a photograph of the 200-inch in the winter of 1958. You'll see a small dusting of snow. This year in California, we've had lots and lots and lots of rain and snow in the mountains, and the photograph there is probably a typical view of what the observatory looked like this winter. Lots of snow and fog and so on. So just very briefly, I'll describe the construction of the 200-inch telescope. Starting around 1936, you see the clearing of the site, preparation of the site. A year later, you start to see the base that's going to support the dome under construction. Another year or so, you see the dome is completed. You see painters are painting the dome. By 1941, if you look inside the slit in the dome, you'll see the actual telescope structure. So the structure is already prepared. If you now go between 1936 and 47, here you see a photograph of the optical shop at Caltech where the 5-meter mirror was actually polished. The mirror was produced by Corning in New York. It took them several years to successfully produce a blank of this size. They had to learn how to do that. It was the largest blank ever produced at that time, and then polishing took 11 and a half years. It shouldn't have taken that long. There was an interruption during World War II, so you could subtract a few years from that, but it's still a long time. And then finally, in 1947, the mirror was transported from Caltech in Pasadena, California, to the Mount Palomar site, and here you can see it was quite a parade taking this through the highways and streets of California. So this all leads up to the dedication ceremony in 1948 in June. So that's now 75 years. So we're celebrating the 75th anniversary this year. One of the reasons I decided this would be a good topic for my presentation. And here you see the ceremony. You see people gathered to celebrate the completion of the observatory and the telescope. And here you see some rather soaring language that was part of the speech given by Raymond Frostlick. Here you see listed as the president of the Rockefeller Foundation. It was the Rockefeller Foundation that provided the funds to construct the telescope. You may know John David Rockefeller was the richest person in the United States and, of course, the world at that time. His wealth derived from Standard Oil, so the largest oil company in the United States at the time. So it was wealth from oil that funded this telescope. And here you see what Raymond Frostlick is saying. As I said, rather soaring language. There's nothing which so glorifies the human race or lends it such dignity and nobility as the gallant and inextinguishable urge to bring this vast, illimitable complexity within the range of human understanding. In the last analysis, the mind, which encompasses the universe, is more marvelous than the universe which encompasses the mind. Astronomically speaking, said the philosopher, man is completely negligible, to which the psychologist answers, astronomically speaking, man is the astronomer. So here you see a rather philosophical description of what astronomers in soaring language to describe the purpose and goals of building such a large instrument. Now moving on to the Keck Observatory, here you see a nice nighttime photograph. You see the stars, you see the band of the Milky Way, you see that there are actually quite a number of observatories on the summit of Mauna Kea. Here are the two Keck telescopes, the largest telescopes on the mountain, 10 meters each. We're now celebrating the 30th anniversary of the Keck Observatory. It's been 30 years since the first of these two telescopes started delivering science in May of 1993. And here you see another quote, this time from Richard Dawkins, describing his feelings about the observatory. Here's what he says: "A great observatory like the Keck is one of those human achievements which, like the Large Hadron Collider, the Human Genome Project, William Shakespeare, and Franz Schubert, render me tearful with pride at belonging to the species Homo sapiens." So perhaps a little less soaring, perhaps a little more introspective, but still a feeling of the appreciation of the significance of the achievement of constructing these instruments. So here's a photograph that I took from the summit in 2015. You can see this is sunset. It gives you an impression of what things look like from the summit when the sun is setting and you may be preparing for nights of observing. You see all the clouds below, most importantly. It's better that they be below the observatory than above, so that's a good thing. You see also a little snow. It does snow on Mauna Kea in Hawaii. People actually, when it snows enough, go skiing. This year has been a good skiing year in Hawaii. You see that in the upper right, the island of Hawaii, where Mauna Kea is the largest island of the Hawaiian island chain. If you don't like being at an altitude of over 4,000 meters, instead you can be at sea level at a very nice resort, which you see pictured there in the middle, and you can go spend your time on the beach, as you see my wife doing in that bottom picture taken in 2022, last year. Here's what the Keck Observatory looks like if you're driving up the road. You can see the row of vehicles parked in the front. It starts to give you a sense of the scale of these domes. And then inside, of course, is the 10-meter telescope itself. You see that the primary mirror is segmented. It's no longer like the 200-inch monolithic mirror made out of one piece of glass. It's made out of 36 pieces of glass, each of which has been polished to have the surface that's needed at the location where that segment sits in the primary. This technique of constructing segmented telescopes is the brainchild of Jerry Nelson, who was an undergraduate at our university, Caltech, and like myself, got his Ph.D. at UC Berkeley. He started this work on segmented telescopes while at Berkeley in 1977. And I'm sorry, the slides are advancing too quickly. And by the early 1990s, had managed to turn his vision into reality. You see the other two gentlemen sitting here developed other methods for building large telescopes. Roger Angel in the middle developed a method for constructing even larger monolithic telescopes, 8 meters in size, by spinning the furnace where the glass, the melted glass, is contained, and slowly allowing that spinning furnace to cool, and therefore the glass achieves a shape which is reasonably close to that required for the final telescope, so you don't have to spend quite as much time polishing as it took for the 200-inch. And then on the right, you see Ray Wilson, who developed a different technology of very thin mirrors with a support structure which dynamically adjusts itself to preserve the shape, the required shape. That technique is used on the European very large telescopes in Chile. However, it's the segmented telescope approach which is going to be the primary approach for the next generation of large telescopes, such as the 30-meter telescope. So the Keck telescope played an important part in the 2020 Nobel Prize. Here you see awarded to Reinhard Genzel and Andrea Ghez. Reinhard Genzel was when I was a Ph.D. student at Berkeley, he was my faculty advisor. He was the person responsible for tracking my academic progress. And I guess that challenge didn't stop him from winning a Nobel Prize. Andrea Ghez was a graduate student. When I arrived on the faculty at Caltech, she was finishing her Ph.D. She moved on to UCLA, where she did her work that won the Nobel Prize. Reinhard and Andrea won the Nobel Prize for their studies of the motions of stars around the center of our galaxy, which contains a black hole whose mass is of order 4 million solar masses. These stars have orbits that are very strongly influenced by the gravitational potential produced by that black hole, and by studying the orbits and the motions of these stars, you can learn about the gravitational potential. You can set limits on the mass density that must exist, and you can then therefore prove that there is no other object that could produce the gravitational potential except for a black hole. In order to be able to see these stars, you have to work in the infrared. The dust in the galaxy, in the Milky Way, prevents you from seeing the galactic center at visible wavelengths. In order to very accurately measure the orbits, it's necessary to use adaptive optics to remove the distortions produced by the turbulence in the atmosphere. So this is the technique where you have a deformable mirror, which a computer adjusts the shape of this deformable mirror about 1,000 times a second to remove the wrinkles in the wavefront imposed by the turbulence in the atmosphere above the telescope. So rather sophisticated technique. And one of the things that often you need to do is to provide an artificial star to use to measure the corruption of the wavefronts by the atmosphere. Those artificial stars can be produced by projecting lasers through the atmosphere and using the sodium layer at about 100 kilometers altitude to produce this artificial star. So here you see the two Keck telescopes with these lasers visualized. This was the development of this technique at Keck was led by Peter Wazinowicz, played an important part in Andrea Gez's work. And then, of course, you need a camera that works in the infrared, which was constructed by these two people, Tom Seufer and Keith Matthews, both at Caltech. Important ingredients in Andrea's work. And of course, this is all leading up to the 30-meter telescope, which will be a segmented telescope with many more segments, smaller than those used on Keck, but basically the same concept. So let's talk a little bit about history, about the history of Palomar Observatory especially. And the key figure in that history is this George Ellery Hale. You can see his portrait on the right. He has the amazing distinction, I believe, of being the only person in history to have built sequentially the world's 3 largest telescopes. The first that he built was Yerkes, which you can see was a 40-inch refracting telescope in Wisconsin, this part of the University of Chicago. He left Chicago, came to California, and then built a 100-inch telescope on Mount Wilson. It was the largest telescope when it was completed. And then he started the 200-inch telescope project. He passed away in 1938 before the project was completed, but he was the key person in getting that project going. Okay, I've got double microphones, double trouble. Mount Wilson, of course, is very close to the city of Los Angeles, and the lights from the city, the light pollution, make it not a very good site today for optical astronomy. But for infrared astronomy, the lights really don't pose much of a problem. Here you see an infrared interferometer that was built on Mount Wilson more recently in 1989, and it worked through the 1990s and early 2000s. And this was a project that was led by Charles Townes, who, of course, received the Nobel Prize for the maser and the laser in 1964. He was a Caltech Ph.D. in 1939. And I show this photograph on the right when I'm lecturing to undergraduate students, trying to give them a little inspiration, because here you see Townes at the age of 95 cleaning the mirror that he's going to use because he's going to stay up all night observing on Mount Wilson, and he's still doing this at the age of 95. It's to me an inspiring photograph, dedication to science. And Mount Wilson is a place that I go to. It's close enough to my house that I can ride my bicycle up. It's a challenging climb for somebody of my age, so I cheat. I use an e-bike, an e-mountain bike, but it's a lot of fun. When you get to the top, you see the sign of the observatory. You see the big transmission towers for TV broadcasts, television broadcasts. Another way to get up there, which is also a lot of fun, perhaps a little less exercise, is to take a motorcycle. That's also a lot of fun. I enjoy doing that. Here you see Mount Wilson a couple of years ago, and you see there's a rather large fire burning in the mountain behind the view you see here. This was taken by our friend, our daughter's friend, I should say, our daughter's classmate, who is both a photographer and a pilot. And so he took this photograph of the fire when it was burning. You can see our home in the foreground, and you can see the towers, if you look closely, the television towers I showed you in the background. And so this was a rather scary moment where it seemed possible that the observatories on the top of the mountain might burn down, and we might lose those really precious historical artifacts. Here's a photograph of me in 2019 at the observatory. You see the Hooker telescope. This also was a philanthropic donation to build this telescope from Andrew Carnegie, who derived his wealth from steel primarily, and it was the second industrial revolution that he was involved in after steam, the first industrial revolution. And here you see a photograph of Edwin Hubble using the 200-inch telescope to discover the fact that the universe is expanding. Completely changed our conception of the universe and the cosmos. And attending this meeting in 2019 that I was at was the grandson of George Ellery Hale, Sam Hale, who's very interested in the history. He's very interested in his grandfather's legacy and preserving that history, and he's very active at the Mount Wilson Observatory. So here you see Edwin Hubble's discovery. On the horizontal axis is the distance to a galaxy. On the vertical axis is the recession velocity, the velocity that the galaxy is moving away from us. And so you see the further away you go, the further away the galaxy is, the faster it's moving away. So you could say, well, these galaxies are just moving away from the Earth, but you have to realize that after Copernicus, we no longer think that the Earth is a particularly special place in the universe. If it's happening here, it must be happening everywhere in the universe. And so that must mean that the universe is expanding. The entire universe is expanding. The slope of that line is a number that the astronomers call the Hubble constant, H naught, H subscript 0. Measuring the Hubble constant has been an important goal for astronomers for quite a while. Hubble didn't get that slope exactly right. The distances he was plotting weren't exactly right, and it was the 200-inch telescope that really cleaned this up. First of all, an improvement in the calibration of the distance measurements using variable stars was done by Walter Baade in the 1950s, and then a little later and going into the 1960s, the use of that improved calibration to get a better measurement of this expansion rate was performed by Alan Sandage, and the number that he derived in the 1960s is pretty close to the accepted value today. It's not very far off. The idea that the universe is expanding gives you the idea that if you go backwards in time, it must have been smaller, that there must have been a big bang. Really strong evidence for that came in 1965 with the discovery of the cosmic microwave background by these two gentlemen at Bell Laboratories. It was more or less an accidental discovery using the horn antenna that you see on the right. And then in subsequent years, the measurement, especially the imaging of the subtle variations of the intensity of the cosmic microwave background on the sky, has led to the conclusion that we live in a flat universe, that the geometry of the universe is flat. The universe is not curved, it's flat. A curved universe would be allowed by Einstein's general relativity, depending on what the parameters, cosmological parameters are, but it turns out the universe is flat. These splotches that you see in the images produced by WMAP and Planck are very small variations in the intensity of this 3 Kelvin cosmic microwave background of order tens of parts per million. It's a rather difficult measurement to do. The characteristic sizes of these splotches is the information that's used to derive this conclusion about the flat universe. And so we're led to the following history of the universe, which is now, you could say, the standard cosmological model. It begins with a very small, a very hot universe, and then suddenly, when the universe was very young, very roughly of order 10 to the minus 30 seconds old, the universe undergoes a period of inflation where the size of the universe expands by some 50 orders of magnitude. It's just an amazing thing to think about. That's called inflation. And then at a time when the universe is not quite 400,000 years old, the universe has cooled enough so that the material stops being ionized and the electrons are captured by the protons to form hydrogen atoms. At that point, the universe becomes transparent, and you can see through the universe. The cosmic microwave background comes from the time when that happens, when electrons and protons recombine to make atoms. It's not possible using electromagnetic observations to see much past 400,000 years when the universe was 400,000 years old. There are techniques, however, that may allow us to get all the way back to the period of inflation using various tricks. But what happens after that is that on this graph is a rather gradual expansion, but then at the end you see the expansion is starting to accelerate. During this whole period, what happens is that under the action of gravity, the small density perturbations that you see in the cosmic microwave background, they become larger and larger. Gravity amplifies these density perturbations. That leads to the formation of stars, galaxies. Eventually, galaxies come together to form clusters of galaxies that are gravitationally bound, and that leads to the universe that we see today. So this idea that the expansion is accelerating was really demonstrated by the late 1990s using measurements of supernovae. These are exploding stars, and the idea is that if you look for a particular kind of supernova known as type 1a, you can use it as what's called a standard candle. You can calibrate its expected brightness, and then by looking at the apparent brightness, you can derive a distance by measuring the recession velocity spectroscopically, looking at the galaxy that contains the supernova, measuring its spectrum, looking at the shift of the spectral lines compared to their known rest wavelengths. You can derive what's called the redshift, the factor by which the wavelengths have shifted longer. And by making a plot, very much like Hubble, except now the axes are reversed, velocity is horizontal, and the distance as measured by the observed brightness is vertical. And by looking in detail at where the points lie, you can see that they lie above the red line that says without vacuum energy, and there's a line that says with vacuum energy that goes through the points much better. That is basically the conclusion that the universe, the expansion of the universe is accelerating. This leads to the following picture. The microwave background measurements that say that the universe is flat, that basically constrains the sum of the density of dark matter and the density of dark energy. The sum of the two has to equal 1 in these normalized units, whereas the fact that the universe expansion is accelerating means that the dark energy, which essentially leads to a repulsion, leads to the universe wanting to accelerate its expansion, has to be larger than the dark matter density, which under gravity wants to pull the universe together. And so if you try to increase the dark matter density, you have to have more dark energy density, and so you end up with a constraint that goes in the orthogonal direction from the flat universe constraint. And the intersection gives you the universe that we live in, which turns out to be consistent with independent measurements of galaxy clusters, and I'll talk about that a little bit later. So this led to a Nobel Prize in 2010, the fact that the universe's expansion is accelerating. The idea of using supernovae in this method for measuring distances, using them as standard candles, goes back to two Palomar astronomers, Walter Baade and Fritz Zwicky. And then in 2010, you have the Nobel Prize for this work. And it's really the points at higher redshift that really allow you to better distinguish between these models. The difficulty is that as you go to higher redshift, you're going to larger and larger distances, which means that the galaxies are fainter and fainter, which means it's becoming increasingly difficult to make the spectroscopic measurements, which means you have to have a larger telescope. What that means is you have to use Keck, the 10-meter telescopes in Hawaii. Here you see the instrument, the low-resolution imaging spectrometer, which performed these measurements. Conceptually, it's a pretty simple instrument. It's a grating spectrograph. You take light in from the telescope, use a diffraction grating. In this case, it's in the form of a grism, which is that element right there. It's a transmission grating on a prism on a wedge so that you can remove that optical element without changing the optical path. You can use this instrument both as a spectrograph with the grism, or if you remove it, you can use it as an imager, a camera. So that's the reason you do that. These cameras that you see here, there's two of them. There's one for the blue wavelength region, one for the red. There's a dichroic that splits the light. The reason for doing this, having two channels, is to increase the optical efficiency. You can tailor the optical coatings on the lenses and optical components for each wavelength band and get overall higher throughput. And you can see that these are rather large lenses. The design and manufacture of these lenses is rather challenging. They're large optics. And here you see the detector cryostat, liquid nitrogen cryostat, that cools the CCD detector in this instrument. And so here we have the recipe for our universe. It's a little over 2/3 dark energy, a little under 1/3 matter. Matter comes in two flavors. Dark matter, which we cannot see, does not interact electromagnetically, and then the ordinary baryonic matter that we're all made of. And the ratio is roughly 5:1 between dark matter and ordinary matter. So this is the amazing conclusion that all the matter that physicists have studied for the history of physics is a tiny fraction of what's out there in the universe, and we really don't know very much about those other two things, the dark matter or the dark energy. The idea that there was dark matter goes back also to Fritz Zwicky, an astronomer at Caltech in Palomar. Here you see a paper that he wrote in 1937. He was studying this cluster of galaxies and studying the motions of these galaxies by measuring the dispersion, the RMS, the root mean square line of sight velocity of these galaxies, and by using the virial theorem to derive what the gravitational potential must be in this cluster of galaxies, he was able to show that this cluster of galaxies must contain much more mass than you could account for in the visible light produced by the galaxies in this cluster. So that was the first paper to start talking about this missing mass problem, this dark matter problem. In the 1960s and 70s, Vera Rubin was a pioneer in this area, studying individual galaxies and measuring the rotation of the stars about the center, and was able to show that their orbits were too fast to be able to be explained by the mass contained in the stars, in the galaxy. There had to be extra matter, there had to be dark matter. So now it's a well-accepted result, observationally, that this dark matter must exist. Of question is, what is it? Physicists have been looking for it. One idea was the so-called weakly interacting massive particle, which some theories of particle physics that invoke supersymmetry included, so it's thought to be perhaps a natural candidate. Big experiments have been mounted, as you see pictured here, deep underground, using either liquid xenon or cryogenic detectors cooled to 100 millikelvin or lower. They haven't found anything. They've been looking. The experiments keep getting larger and larger, but the WIMP hypothesis seems to be getting less and less likely that that's the answer. An even more wild idea is that you have black holes that were produced in the early history of the universe. This is an idea that Stephen Hawking proposed a long time ago, that it would be possible that in the early universe you could have fluctuations where the matter density in some point was large enough to trigger gravitational collapse. And by now, there's all kinds of mechanisms that have been proposed, just a whole zoo of different ideas about how these primordial black holes might be produced. And the question is, observationally, can we eliminate some of these possibilities? So one way to think about this is in terms of the mass, the characteristic mass of these primordial black holes, and what observational constraints can be put. So here you see in the blue, there are rather good constraints on black holes of those masses. I have to put on my glasses to read the scale here, but you can read it. Of order 10 to the minus 5 solar masses, it looks like. Experiments, there was an experiment in the 1990s called MACHO. Massive Compact Halo Objects was the clever acronym, where they looked for events where if you had a large camera staring at the sky looking at a large number of stars, if these primordial black holes existed, it may be possible that a black hole would cross in front of one of the stars, and through gravitational lensing, through the bending of the starlight by the gravity of the black hole, you'd see an increase in the brightness temporarily. And by measuring that, you might be able to infer that a black hole crossed in front of the star. If you saw enough of these events, that could be proof of existence. Well, they didn't see very many events, and so they are setting limits on how much of the dark matter might be in these black holes, and it basically rules out the idea that the dark matter is black holes, at least in this mass range. Another interesting constraint for much lower mass black holes comes from something labeled V here on this plot, which turns out to be the Voyager spacecraft, which I know a little bit about because in the 1970s and 80s as an undergraduate student at Caltech, I worked on a little piece of the Voyager project. I was responsible for processing the calibration data for a cosmic ray electron spectrometer that was flown as part of the cosmic ray instrument package on Voyager. Here you see the report that I wrote way back then. Leading the group that I was working in was Ed Stone, who was the project scientist for Voyager. My mentor directly was a graduate student by the name of Neil Garrels, who became quite famous in astrophysics. He led a space mission known as SWIFT. The Space Observatory is now named for him. It's the Garrels Space Observatory. Well, that spacecraft was launched in 1977, about 2 months before I started Caltech as an undergraduate, and by 2013 it had left the solar system. It had gone into interstellar space. And here you see the paper in Science magazine reporting this fact that it had gone into interstellar space. You can't see the, looks like something happened to the graphic up top, but the bottom is showing you the spectrum of cosmic ray electrons that Voyager is measuring. And it's those measurements that are giving limits to the possibility of these fairly low mass primordial black holes. Because as Stephen Hawking demonstrated, black holes emit Hawking radiation. You can assign a temperature to a black hole. And black holes, if they're small enough, can evaporate by emitting this Hawking radiation. And if so, they simply just disappear. Well, if you have these primordial black holes and they're emitting Hawking radiation, they're going to be emitting electron-positron pairs. And if they existed, then the cosmic ray instrument on Voyager would be capturing the electrons and positrons emitted by the black holes, and being away from the solar system and being away from the influence of the sun's magnetic field gives you the possibility that those electrons and positrons might actually be able to propagate from where they're emitted to the Voyager spacecraft and thereby be detected. The fact that Voyager is not seeing them means that they don't exist. That leads to that constraint labeled V for small mass black holes. But there's this window in between which still is not very well constrained. And it leads to the idea that perhaps there might be black holes in this mass range, and you can start thinking about what they might do. In particular, you might think about what would happen if those black holes interacted with a star. It turns out that the black holes in this mass range could pass right through a star without really doing very much to them. The black hole would slow down, which means that eventually it would be captured. It would slowly spiral in, and eventually it would be captured by the star, and it would sink to the center of the star. And theorists tell us that you wouldn't really be able to tell. Nothing would really change about the appearance of the star for a long time. The black hole would just sit in the center of the star. But in about the last 10 minutes of the lifetime of that star, the star would simply disappear. It would simply be swallowed up by the black hole. So imagine that that happened to our sun. You're walking around one day. It's a normal day like today. The sun is shining, beautiful. 10 minutes, it's dark, the sun is gone. It's a scary thought. So I have a colleague who's interested in looking for the possibility of that stars simply disappear. And to do that, you need a large survey, a large imaging survey, and you want to see, did some star go missing out of all the huge numbers of stars you're looking at? That colleague is Peter Fisher. He's a friend. He's the former department chair in physics at MIT. And he's going to start looking for disappearing stars and data collected by something called the Zwicky Transient Facility. So I'm going to tell you about that, ZTF, in a little bit. But before that, I'm going to tell you about what led up to the ZTF. Here you see Fritz Zwicky using the 18-inch telescope at Palomar. And he's doing very early work on supernovae. He's really the person who perhaps invented the term supernovae. He discovered a number of supernovae. He's very interested in them. He proposed the idea that supernovae were responsible for producing cosmic rays. Well, that turned out to be a correct conjecture. By 1948, an even larger telescope similar to the P18 was built. This is the 48-inch Schmidt telescope. This is of a design that allows you to capture a very wide field, so you use it for photographic surveys of the sky. It's able to capture a large solid angle of the sky, and you can use it to map the sky. Great for doing surveys. So after this telescope was built, the National Geographic Society sponsored an all-sky survey that became very famous. Basically, every observatory in the world had a copy of the plates produced by the survey, so they could use them as a atlas to the sky. And here you see one of the astronomers that was involved in that survey, George Abel, who, among other things, produced a catalog of galaxy clusters that were found in that all-sky survey. So today, the 48-inch telescope has become the Zwicky Transient Facility that I promised to talk about I mentioned the disappearing stars and using ZTF to try to find them. Well, we no longer use film, we use CCDs. And so ZTF basically is putting in the largest CCD camera that you can fit into this telescope and then using it to do automated robotic sky surveys. You can see a filter in front of the CCD camera, and over to the side you see a robotic arm. And so many, many times a night, this robotic arm goes in and pulls out a different filter from a cassette and changes the filter so you're taking images in multiple colors, and you map the sky. It has a very large field of view, it goes very fast, and you can discover all kinds of things like supernovae, explosions, stars exploding. You can try to look for electromagnetic counterparts of gravitational wave events. You can use the supernovae to study cosmology, as we talked about. You can look for things known as tidal disruption events, or TDEs, where a star falls into a black hole, it meets its death. Oh boy, what gory subjects. You can look for binary stars, stars that are very close, pairs of neutron stars whose orbital periods are measured in minutes that are potentially very interesting gravitational wave sources. You can look at the solar system. An asteroid, the first asteroid discovered inside the orbit of Venus was recently discovered with ZTF. And so there's all kinds of things you can do with a camera and telescope like this. And this is just the latest of many, many surveys that have been performed with this telescope. And here you see the results from ZTF. Different color points mean different things. The largest number of points are at the top. They're regular Type 1a supernovae, but you'll see sprinkled in things like these tidal disruption events and so on. But in order to figure out what a particular event actually is, it's very often necessary to obtain a spectrum. And you can look for various spectral lines and use those spectral lines to classify the event. And in order to get those spectra, you very often have to turn to the 200-inch to gather enough light to get a detailed enough spectrum. And so that's what the 200-inch today spends a lot of its time doing. And the main workhorse instrument for all of that is very old. It was built in 1982. It was built by two very well-known astronomers, Bev Oak and Jim Gunn. Again, it's a fairly simple instrument. It's a grating spectrograph. It has a red channel and a blue channel. It was one of the, I believe it was the first spectrograph on the 200-inch using CCD detectors. So that was a big, important step in terms of spectroscopic capability of the observatory. This was at a time when CCD detectors were just being introduced into astronomy. Of course, those detectors go back to 1969, invented at Bell Labs. Here's the first time they were used for astronomy in 1976, described in this Sky and Telescope article in 1987. The first CCDs used on the Hubble Space Telescope were very small, 800 by 800 arrays. Eventually they got much larger. Here you see a 2K by 4K. And the work developing these CCDs, much of that work was performed at JPL, the Jet Propulsion Laboratory where I worked. There's this big, thick book published by Jim Janicek that did a lot of this work describing all of that. Of course, that led to the Nobel Prize for the invention to Boyle and Smith. And so here you see a photograph of what's happening at the 200-inch in 1987, this 4-shooter camera. This was basically a prototype for the first CCD camera that flew on Hubble, the WIFPIC instrument, the Wide Field Planetary Camera. In fact, Jim Gunn and Jim Westphal that you see pictured there that put this camera on the 200-inch were the people who proposed constructing that camera for Hubble. And here, Jim Gunn very humbly deflects any credit for this work on the 4-shooter to the people that really worked hard to develop the CCDs, Morley Bloch and Jim Janicek. And here you see a photograph of an astronaut removing the original WIFPIC instrument to install later on the WIFPIC 2, which corrected the problem that Hubble had with spherical aberration in its primary mirror. Today, we're replacing that old 1982 instrument. We're building something called the next generation Palomar spectrograph. It's going to have 4 channels instead of 2 channels. We're trying to squeeze out even more efficiency by subdividing the wavelength band 4 ways and really highly optimizing the coatings, etc. We're making good progress. You can see the structures getting built, the detector cryostats. We have the acquisition and guide system for this instrument installed just at the end of March for the first tests at the 200-inch. We're hoping to have this instrument commissioned in about a year's time. We're continuing to build instruments for Keck. Here's another spectrograph, the so-called KCRM. This is what's called an integral field spectrograph, where you take a patch of sky You split it up into a two-dimensional array of pixels. You use optics to reformat those pixels into a long slit, which you then pass through a standard grating spectrograph, and you essentially are obtaining three-dimensional, your two spatial dimensions and then the spectroscopic dimension. You're obtaining three-dimensional images of things in the universe, galaxies, and so on. One of the things that it will be used to study is highly redshifted emission from hydrogen atoms, the principal 2-to-1 transition, which astronomers call Lyman alpha, with a wavelength of 1216 angstroms. You might be interested to know that the address of the building that I work in is 1216 California Boulevard. That's not an accident. We're also building other instruments. There's the Keck Planet Finder, which has now been commissioned. I won't go through this all in detail, but you must know about the radial velocity method, where if you have a planet orbiting a star, well, the star is doing its own little orbit about the center of mass. The ratio of velocities of the planet's orbital velocity to the stellar orbital velocity goes as the ratio of the masses. In the case of the Earth and Sun, that ratio is about 3 × 10⁻⁶, which means the motion of the star is very small. It's very difficult to measure. The spectral lines from the star are shifting very slightly, and the name of the game is to be able to, over a time scale of many years, have an instrument that's stable enough to be able to measure very small variations of the wavelengths of the features, the spectral features from the star, to be able to infer the presence of planets orbiting that star. Uh-oh, now I'm in trouble. So to make the instrument stable, KPF uses an optical bench made of zero-dur. It's a very low thermal expansion material. Here you see the camera. There's an Herschel grating for high spectral resolution in back of the camera there. Here you see a photograph of what this new instrument looks like in the basement of the Keck Observatory. The light is first captured from the telescope and injected into multi-mode optical fibers, which transport the light from the telescope down through the telescope structure, down into the basement to the location of the spectrograph. The reason it's down in the basement is that that's a very stable location, both seismically and thermally, and you have to take great pains to stabilize the instrument to be able to see these very, very weak shifts. And here you see the team celebrating the first light with this new Keck Planet Finder in November of this year. Last year, I'm sorry. There's another instrument that recently passed its preliminary design review. It's starting to undergo construction, known as HISPEC, which is going to be working in the infrared. Like KPF, the light will be injected into an optical fiber, except this time adaptive optics will be used to reduce the light to a single transverse mode, so it can be transported by a single mode optical fiber. The Keck Planet Finder does not do this. It does not use adaptive optics. It suffers from the turbulence in the atmosphere. It has to use a multi-mode optical fiber to do the optical transport. In HISPEC, by working in the near infrared and using adaptive optics, the light will be injected into a single mode optical fiber, again transported to now, in this case, an infrared spectrograph deep in the basement for the same reasons. This instrument, in addition to doing the radial velocity measurements, will attempt to characterize the atmospheres of exoplanets. It will attempt to be able to collect light from a planet very close to the star, isolate the light from the star, and try to look for spectral features in the planet's atmosphere. Features that come from water or ammonia or methane, molecules made using the abundant elements, and try to start learning something more about these planets other than their mere presence. I'm just about done. There's one more instrument that's coming. It's in even an earlier stage. It's a replacement for this low-resolution imaging spectrograph that I mentioned that did the measurements of the supernova redshifts. That instrument is now 30 years old. It's wearing out. The mechanisms are giving trouble. So we're going to have a nice new instrument coming. And all of this is enabled by a rather large gift we received for this purpose about 2 years ago, a gift of over $70 million to be building all these complicated instruments. And speaking of gifts, I'd like to mention Gordon Moore. He's had a very large impact on astronomy at Caltech. You all know him for Moore's Law, the famous prediction about what would happen to integrated circuits. He is a Caltech alum, received his Ph.D. there. He has supported the instruments I described, KCRM, KPF, HiSpec, with personal donations as well as donations from his foundation. And he has donated several $100 million towards the development of TMT. He's really had a large impact on astronomy. Here's a photograph of Gordon Moore in Hawaii in 2014 at the time of the creation of the TMT partnership. Behind him, you can barely see, is Ed Stone, the Voyager project scientist who until recently served as the executive director of the TMT project. And we're hoping that the National Science Foundation in the United States will join the project and provide the remaining funding that's missing. We received a strong endorsement in the decadal survey that was published in 2021, and hope to be able to turn this photo into a reality. Thank you.
Thanks a lot for a beautiful talk. We have time for a couple of questions. Yeah?
So for astronomical observations, imaging, is the CCD still the most best technology available, or are there some newer developments?
Yeah, so astronomical instruments that work at visible wavelengths continue to rely on CCDs for the most part. There are some competitors, CMOS imagers, for instance. The story of the CMOS imager starts actually at JPL. It was invented there, as it turned out. The motivating factor was cameras for planetary missions, but then it's turned into a huge business. That's what your cell phone uses, is a CMOS imager. The difference between CCDs and CMOS is that in the case of a CCD, you basically clock the charge across the surface of the chip, and at the periphery of the chip there's an amplifier that reads out the charge, and the actual charge itself is physically transported across the surface of the chip to reach the amplifier, and then once it's amplified you have wires that carry it out to your electronics. In the case of a CMOS imager, you actually have transistors associated with every pixel. And so the amplification is performed on a pixel-by-pixel basis. And so the challenge is to produce a low enough noise amplifier that's small enough to fit within the individual pixels. And so there's been great progress in CMOS imagers. The noise of CMOS imagers keeps getting better and better. They're starting to become competitive. It'll be interesting to see how that develops in the coming years.
So,
thank you for a very interesting talk. So you've been talking about the ground telescopes. Do you think the future belongs to the space telescopes for future astrophysical observations?
So we have the magnificent launch of the James Webb Space Telescope, which hopefully you all saw and paid attention to. In fact, just before coming to Lithuania, and part of the reason why I had to work hard to get this presentation ready for you is that I was asked to come to NASA headquarters to give a presentation, and without a lot of lead time, so I had to squeeze in preparing a whole other presentation for a whole different audience. And in that presentation, I was talking about what might be happening in space in the area of far-infrared astronomy. This is really my field, and I'm very interested in seeing NASA pursuing far infrared mission in the future. There's a couple of possibilities. I served on a study team that studied a large mission, a so-called flagship mission that might cost, say, $5 billion to build, that would be working in the far infrared. This is known as the Origin Space Telescope. But in my view, it would be better to do a smaller mission first, in the roughly $1 billion class, which NASA calls a probe class. And the leading contender in terms of detector technology for that mission is the technology that Gintaras mentioned that I played a role in inventing, the so-called superconducting kinetic inductance detectors. So I'd very much like to see that mission go forward. NASA is calling for proposals, I believe, this year. We'll see how all that plays out. It would be wonderful to see that mission go forward, but you know, it's a tall challenge to be able to win these competitions, so we'll see how that goes. But in terms of visible or even ultraviolet telescopes for space, it's very likely that the next large flagship telescope for NASA will be a large telescope working in the ultraviolet through near-infrared range, particularly motivated by this desire to study exoplanets and to do a better job of characterizing exoplanets. The difficulty with working from the ground, I mentioned, is the turbulence in the atmosphere and the need to use adaptive optics to remove the turbulence. If you're trying to study exoplanets, you have a very fierce problem. The light from the exoplanet is of order 1 billion times fainter than the light from the star, and yet the two objects are very close to each other on the sky. You have to suppress the light from the star without blocking the light from the exoplanet. And if the atmosphere is dancing around and you're trying to correct for the atmosphere 1,000 times a second, it's very difficult to do that job to the degree that's needed to get to this 1 billion to 1 contrast ratio. So from the ground, projects like the 30-meter telescope will be contributing significantly to the study of exoplanets, but it's very unlikely that they'll reach this 1 billion to 1 contrast ratio. For that, you'll need to go to space to get the stability of a telescope in space, the lack of the turbulent atmosphere in space, and so that is going to be a very interesting future area for space telescopes.
The last one.
I would like to ask a question more about observations side at the observatory. So at the start of your talk, you showed a picture of observatory all covered in snow. And I would like to ask, in the recent years, how many clear nights does the observatory get per year?
Well, that answer, of course, depends on the year and depends on the location of the observatory. Mauna Kea, I think, enjoys better weather than Palomar. Palomar is usually, I don't know that I could give you a typical statistic. What I can tell you is that in both cases, Mauna Kea and Palomar, this has been a very bad winter for observing, because the same storms that come to California apparently come to Hawaii first and dump snow on the summit, and then they come and they dump snow on Mount Palomar. And so it's been a record year in terms of precipitation in California. And right now at Palomar, we're suffering because we accumulated 5 or 6 feet of snow, and then shortly afterwards the temperature went up a little higher, and instead of snowing, it rained. And then the rain melted all the accumulated snow, and all that water had nowhere to go. Much of it went into the ground. But what we're seeing is in the little museum that we have where we accommodate visitors, we have tens of thousands of people visiting, the public visiting the observatory on a given year. And that's where they go. That's where you see the exhibits, that's where the restroom facilities are, that's where you stop before taking a tour to see the 200-inch, for instance. We need that facility to be able to accommodate tourists. Well, with all this water in the ground, it's coming up through the foundation, through the concrete foundation, There's just water seeping up out of the ground, and the floor is flooded. The walls of this museum are wet. We have a big problem. We have to fix the museum so that we can bring in visitors. So the answer is this year it's been challenging. It's been challenging at Mauna Kea too. This KCRM instrument that I mentioned, they had to ship all their equipment to Hawaii. They had to bring it up to the summit. They had to wait for the weather to clear up before they were able to bring up their equipment. They brought up their equipment, but then they couldn't get up to the summit to start unloading it and using it. Just simply accomplishing work and getting that instrument project going on the summit has been a real challenge just because of the weather.